So, welcome back. So, again we will continue the discussion on this adjoint operator and symmetric operators, and when a symmetric operator is going to be self adjoint, those things we will now discuss. Okay. So, again let me say how we define the adjoint. Okay. So, this y belongs to dA star if x going to AXY, this inner product is continuous. Okay. So, of course, x belongs to dA, and of course, dA is dense. Okay. So, this was essential in order to get this unique element. So, then we have AXY, so relation x A star y. So, this is very similar to the bounded case, only thing is now we have to pay attention to the domain. Okay. So, in particular, if A is symmetric, we see that if A is symmetric, then A star is an extension of. Okay. So, this is clear from the definition, but okay, we say, so this is again definition, A is self adjoint if A and A star are same. Okay. So, again let me stress. So, this means dA is equal to dA star and Ax equal to A star x for all x in dA. Okay. So, here is a result in this direction. So, just I will mention that. So, just before, okay. So some facts. I will write. So, we can compare the graph of A star and graph of A. Okay. So, here is one such result. So, this is very straightforward. Graph of A star is graph of A, but there is a twist. So, I will put this operator V and its orthogonal complement. So, this is V is from H to H cross H2. So, this is Cartesian product. Defined by V of. So, if you take any pair, okay, you just y minus x. There are other definitions, but this is simplest one. Okay. So, that okay, and this is orthogonal complement. So, orthogonal complement of any subset of a Hilbert space is always closed. So, this implies A star is always a closed operator. a closed even if A is not. Okay, so this is one interesting thing. Okay, so A star is even if A is not. Okay. The second one, suppose A is a symmetric operator. Symmetric operator. Then if lambda is non-real, that means its imaginary part is not 0, then norm of A plus or minus, okay, lambda I x is bigger than or equal to okay, imaginary part of lambda norm x for all x in dA. Okay, so this is a straightforward computation you can do. So this immediately says that this operator A plus or minus lambda I, whenever lambda is non-real, is 1 1, but it may not be onto. Okay, so that's where the trouble comes. So when it is onto also, then suddenly it is is going to be self adjoint operator, that we will see that. Okay. So this implies further image of A plus or minus lambda I. Okay, so this is a subspace of H, is a closed subspace if and only if A is closed. Okay, so this identity gives this result. Okay, so this image or range of this operator is a closed subspace if and only if A is a closed operator. Okay, and this gives necessary and sufficient condition for a, so that is third one. Okay, suppose A is a closed densely defined symmetric operator. Okay. So then A is self adjoint. Oh, sorry, y 2. If and only if, so plus or minus I belongs to rho E. So this is resolvent sub. Resolvent set of A. So this means what? Okay, so this operator A plus or minus I belongs to BH. So, there is no speciality about this I. You can take any lambda non real and you put the condition for plus or minus lambda, okay, may be replaced by plus or minus lambda for some non real lambda. Okay. So, this is an important result. So, it tells us when a symmetric operator, of course closed and densely defined, then only we can define the adjoint. So, again you see a condition on the resolvent. Okay, so that is important. Okay, so that is fine. Okay, these are important results. So, if you have studied already, it is fine, otherwise it is time to recall everything. So, we are going to use all these things, okay, in application to PDEs, okay, especially in the case of Schrodinger operator and wave equation. Okay, we will see that. So, one final topic of discussion in this operator theory before we move on to proper semi group theory and then applications to PDE. Okay, so, this is perturbation. Results. Okay, so just so this essentially developed by Kato in the study of Schrodinger equation and also system of hyperbolic equations. Okay, so that's so idea is the following. So, for example, consider the heat equation. Okay, so U T. So, we will treat this as an abstract OD in some function space and we expect a semi group. So, generates a semi group. Okay. We will see that. Okay. So, then if we consider the perturbed equation, U t equal to Laplacian u plus some lower order term. Okay. So, we expect this perturbation by lower order terms not to affect too much and again expect this to generate a semi group. Expect it. Okay. Generates a semi group. Okay. So, this gives an idea how these lower order terms or lower order perturbations should be with the main one. This is the our main operator, okay, and we are perturbing by lower order terms. So, how can we expect again that to generate a semi group? Okay. So, this is the idea behind the discussion of this perturbation results. Okay. Okay. Suppose A and B are linear operators. In H. Okay. So, let us continue the discussion in Hilbert space, okay, and assume dA is a subspace of dB. Okay. So, this assumption makes so that A plus B is defined. At least on dA. It is defined on dA intersection dB, but dA is a subspace of dB. So, its domain of definition is also dA. Okay. If A is closed, this A plus B need not be closed in general. A plus B need not be closed. Close in general. Okay. And same thing we also expect. So, even if A is self adjoint and B is symmetric, this A plus B need not be self adjoint in general. Okay. So, here is one sufficient condition. So, again this is derived by Kato. When that becomes true. Okay. So, this is the definition. We say B is A bounded, okay, A and B as above. So, A and B are linear operators with dA a subspace of dA. If Bx norm is less than or equal to A norm x plus B norm A x for all x in dA. Okay. So, this is for some A B positive. Okay. So, note that this right hand side. Okay. So, if you recall the definition of the graph norm, so this is equivalent to the graph norm of A. So, when A is a closed operator, we know that the space dA with graph norm becomes a Banach space. So, essentially we are asking for B to be a continuous mapping from dA to H, which is continuous. Okay, that is what we are expecting here. So, essentially this means at least when A is closed, B is a continuous operator, bounded operator from dA. So, we noted this with graph norm into H. So, that B is going to be our perturbation. So, this A is our main operator. So, if B is A bounded, then there is a possibility that A plus B will have the property similar to that of A. If A is closed, then A plus B is closed. If A is self adjoint with some additional condition, we expect A to be A plus B also to be self adjoint. Okay. So, here is one more definition. Okay. The let me call it star. The infimum of all B positive for which star holds for some A positive. So, if we change B, then A also may change. Okay. So, that is called the A bound, and in literature you also find the name Kato bound. Okay. Kato bound of B. Okay. So, this definition there. Okay. So, the restriction is on this Kato bound or A bound. Okay. So, when that A bound of B is under control, so nice things happen. Okay. So, let me just state this as a theorem and then okay. So, suppose A, B are linear operators with dA subspace of dB, B A bounded with A bound less than 1. Less than 1. So, these are the assumptions on the operator A and B. Okay. Then the following hold. The first one, if A is closed, then A plus B is also closed. So, just see here we are not putting any conditions on assumption on B. We are not assuming that B is closed. Okay. So, that's the first one, and the next one, this assume A is self adjoint and B symmetric. Okay. So, with these two additional assumptions, then A plus B is also self adjoint. Okay. So, especially the second one, the second part, this is used in the study of Schrodinger operator. This is the main ingredient there, Schrodinger equation with a potential. Okay, let me just simply say that. So, the Schrodinger equation, this du by 1 by I du by dt, this Laplacian u plus Vu. Okay, so, this is the potential. So, this is a function, given function, real valued function. Okay, so, this Laplacian is we are going to with appropriate domain. So, this del is a self-adjoint operator. So, I am not telling you what is the space and what is the domain. So, we will come to that thing, and since V is real valued. So, that certainly this multiplier operator is symmetric. Okay. So, then under some certain conditions on the potential V, this is also going to be self-adjoint, and that is what we want. Okay. Under some assumptions on V. And that is where you require your knowledge in Sobolev spaces and various inequalities. See, essentially we have to obtain such estimates, right. So, here is the definition. So, this star, okay. So, these are going to be some norms in some function spaces, and so the inequalities you would have studied are helpful in deriving such estimates, and then finally you have to show that the Kato bound is controlled and less than 1. Okay. So, let me just make one remark. So, closing remark. So, here we have assumed this Kato bound is less than 1. Okay. So, there are results which will go up to 1, A bound equal to 1. So, for those results, so you can look into this Kato's book. So, one can go up to 1. Okay. So, Kato's book. So, this is quite old book. So, perturbation of linear operators. Title itself. Okay. So, with this essentially recalled whatever we need from this theory of unbounded operators. Of course, in case we need little more, then we can always do at that time, and from next time onwards we are going to study semi groups little bit. Of course, that is also not in full detail. Some will describe various notions and come up to Hille-Yoshida theorem, and after that we will take up the study of PDEs. Thank you.